Okay, today in class we are essentially on page 63 in your notes going to go back one more time to the concept of I say inverse, you say switch. And the biggest reason that we're going to do that is because inverse notation with trig functions gets a little bit tricky. We've actually used the inverse notation quite a bit, and the inverse notation that you are used to seeing would be the inverse notation that reads something like this, where there would be a number in there. And because I've made a switch, the angle value, or theta, becomes the answer, and the number that would otherwise have been the answer becomes part of the question. That's the I say inverse, you say switch piece of this. Now, quick little sidebar note because I can. I want to say that one of the first parts of tonight's homework is going to ask you to be writing equivalent statements. So they may give you a question like, if the sine of theta is rad 3 over 2, write an equivalent inverse statement. Well, all they're saying to you is I say inverse, you say switch. What would the equivalent statement that looks like this say? You're pointing at it, Jewel. Do you not want to speak? That's okay. It would basically look like this, where this number right here would go into the parentheses where I have the number sign. And if you're switching, then effectively the rad 3 over 2 is going to end up over here. Theta is going to end up over here. And the way I made that switch was to call it an inverse. So that's the first part of your homework. It's not at all new. That's not what I'm teaching you today. It's just kind of to tie ideas together, that first part of your homework, to remind you that we've actually already done this stuff quite a bit. What we're going to be focusing on is the difference between an inverse that's a function and an inverse that's not. And those inverses, because there's a difference between them, are given unique names. And those names are, and notice the difference, they're not very different, capital A arc and lowercase a arc. And the only difference between those two is one of them is a function and one of them is not. So arc is going to effectively translate as inverse. This is the inverse function. So when I say I'm looking for an arc sine of a number, I'm basically saying this. I'm looking for an inverse sine of a number. When I say I'm looking for an arc sine of a number, I'm basically or effectively saying the same exact thing. So what's the big difference? What's the big hoo-ha? This one is not a function, and this one is. And I'm going to take just a minute and ask you to just watch as I explain to you what the heck I mean by that. You'll notice before I started recording, I put 2 pieces of graph paper on my next 2 sheets of paper. You're welcome to copy these down, but you don't need to. It's more important to me that you just watch. Because what I'm about to do is I'm about to take a sine graph and I'm going to invert it, reflect it, or switch the x and the y coordinates of a sine graph. That's my goal. Now, in order to do that, I need to keep in mind that up to this point, we've kind of been using different unit scales on both axes. Up to this point, we've been counting along the x-axis in pi notation, or basically counting by pi over 2s, and we've been counting on the y-axis by 1s. If I'm going to be switching, I very much want to be kind of counting the same exact values. So I'm going to be uber rounding to do this, just to give you a sense of picture. Is that okay? All right, so I am going to basically say, I'm going to let this be, nope, I'm not going to do that. I'm going to let this be pi, but I'm going to call it 3. And I'm going to let this be 2 pi, but I'm going to call it 6. Now you can see the uber rounding going on there. Does everybody understand what I mean by that? 6 is nowhere near 2 pi. 2 pi would actually be 6.28. But I'm trying to make this as simple as I can to graph. And so I'll count in the same exact scale going up and down the y-axis And this way, on both axes, every box is worth 1 unit. Is everybody clear on that? Okay, now if I were to draw a sine graph, my sine graph would have at 30 degrees, pi over 6, or, well, let me put in the main values first. At pi over 2, or halfway between 0 and pi, I'd hit a value of 1. At pi, I'd hit a 0. At 3 pi over 2, I'd hit a value of -1. And at 2 pi, I'd hit a 0. So my sine graph would look like this. Now the next thing I'm going to do is extend this, if that's okay with you. I'm just going to keep going. So I'm going to go out 3 more boxes and give me another curve there. And then I'm going to go backwards and do the same thing, so that every 3 boxes I've essentially got a hump. And they will be an upper hump, then a lower hump. So this is a continuation of the sine curve many, many times. Does everybody see how I got that? So that's a sine x. Okay, now if I wanted to invert that, effectively I'd be taking every one of those points and switching them. So the coordinates of those points would kind of get reversed. So 0, 0 would stay 0, 0. But 1.5, comma 1 would become 1, comma 1.5. And 3, comma 0 would become 0, comma 3. And 4.5, comma -1 would become -1, comma 4.5. And 6, comma 0 would become 0, comma 6. So everybody see that inverse graph going on there. Now you can also check it if you wanted to, because we said the other way to tell an inverse graph is with a reflection over the line y equals x. Theoretically, if I did this correctly, it should flip or reflect over that line right onto itself, would it? It absolutely would. So it's kind of a pretty little picture there. Now if I just continue that pattern backwards, this graph is going to effectively do this. This is my, nope, that's not what I meant to write. This is my, oops, hello. Undo, go away. Y equals arc sine, not theta, x graph. And by that, what I mean is this is the graph that represents all of the inverse values, but as I said on the previous page, is clearly not a function. And how do I know very clearly by looking at this graph that that is not a function? Shay? Fails that vertical line test with vengeance. It fails, 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 fails. Does everybody see it? Okay, now keep in mind that that graph, I've only done 2 cycles. I've done 1 in each direction, but I should have done more because I had more here. So let's keep going this way. Is that a little better? This would keep going forever and ever and ever. There would be infinitely many sine graphs going up and down. I like to call this my snake graph. It looks like it's snaking up and down the y-axis. So that's going to fail, 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 fail. And the implication there is that a lowercase a arc sine graph has lots and lots of values. And it does. There are lots and lots of angles that have the sine value rad 3 over 2. Rad 3 over 2 happens everywhere that I can come up with an angle whose reference is equivalent to 60 or equivalent to 120. So as many times as you can go around a circle, forward or backward, and hit those 2 places, you're going to have a rad 3 over 2 answer. There's never going to be a stop to how many different angles you can come up with. And that's going to be essentially what this lowercase a arc sine graph is. Now your calculator, when you hit inverse sine, doesn't give you all of them. It only gives you 1. And that's because on your calculator, the graph is a function. So now I need to go a little bit farther into this, and I need to kind of tell you basically what I've told you before, and that is that your graph, whether you remember it or not, is broken into 4 unique parts, where it's broken at 90 degrees, 180 degrees, 270 degrees, and 360 degrees into quadrants. So that this is the equivalent of quadrant 1, this is the equivalent of quadrant 2, this is the equivalent of quadrant 3, and this is the equivalent of quadrant 4. Does everybody remember me talking about that when we did the original graphing day? Okay, so that means if I were going up and down, vertically speaking, this would be the equivalent of quadrant 1, this would be the equivalent of quadrant 2, this would be the equivalent of quadrant 3, and this would be the equivalent of quadrant 4. If I were to keep going with that, quadrant 4 is also down here. So it would go 1, 2, 3, 4, 1, 2, 3, 4, all the way up from bottom to top. Does everybody see it? Okay, now I need to get rid of those so I can do a little bit of drawing on my graph without making the graph too excessively busy. What your calculator is going to try to do, and I've said this to you before, is it's going to try to keep your answer acute. So it essentially is going to try to take this green snake graph and restrict it so that you hit every answer. Now notice here that these answers all fall between these 2 yellow lines. Every answer is between those 2 yellow lines. So to restrict it just means shrink the height so that I hit every value between those 2 yellow lines without repeating. So what the calculator is going to try to do is make that happen and make sure that you get an acute angle. So since sine is positive in quadrant 1 and negative in quadrant 4, I went too far, it's going to give you all the answers that land in quadrant 1 and all the answers that land in quadrant 4. Now the reason that it's doing that is because that way you've got a negative set of answers right here and a positive set of answers right here. And you've got all the answers covered, but now that graph is a function. Passes the vertical line test. Do you see it? And this graph is known as the arc sine graph. That's the difference. If it keeps going and going and going, it's a lowercase a. If it's only one little section of graph, it's a capital A. If it's not a function, it's a lowercase a. If it is a function, it's a capital A. Now just to be clear, go to your grapher, make sure you're in radian mode, and type in inverse sine of x. Make sure you're in radian mode, and then let's zoom 7. Zoom 7 is essentially zoom trig. It sets your window for a nice trig set of window range. And you see that the graph that the calculator will show you, function or non-function? That's definitely a function. This is the function that I just did right here, which means that capital A arc sine is the same thing as inverse sine. This one is the one that stands alone. This one has no other name. So I can get a lowercase a arc sine by myself using the inverse sine graph, but I won't get it on my grapher ever because my grapher will only graph functions. Still good? Okay, that's going to be the inverse sine graph. I'm going to take just a few minutes now and show you what the inverse cos graph looks like. As you can imagine, it's going to look very much the same. Okay, so this is the graph of cosx and the lowercase a, not a function, arc cos graph. And again, if I wanted to restrict this graph, this is where the problem lies. Because in this graph, remembering carefully, and I'm going to do this in magic pen so it goes away, that this is quadrant 1, below that blue line, and this is quadrant 2, above or between those two blue lines. You'll notice that when I draw in quadrant 4 here, those answers and these answers are identical answers. If I